So, welcome everybody. Today's speaker is Stephan Wojtowytsch from Princeton University, and he will talk about optimal transport for non-convex optimization in machine learning. Please go ahead.
Thank you so much, Armin. Thank you for the presentation. I do realize that this topic is somewhat tangential to geometric analysis at best. So I promise that I will have some geometry in my talk, but otherwise, if that is going to come towards the end. So if that comes too late for you, at least I'm going to try to explain what this machine learning thing that everybody's been talking about is and what we as mathematicians can do in this field. So okay. All right, so I'm going to give an overview over, I think, some parts of machine learning and specifically neural networks. Then I'm going to talk a little bit about why I say non-convex optimization and why a lot of these problems have to be non-convex. Then I will come to shallow neural networks, which is not deep learning, but which is the area where we currently have a bit more understanding. And then I'm going to talk about gradient flow optimization and how we can guarantee that we're actually going to find absolute minimizers of non-convex energies when we are following a gradient flow. And so I think that is a fairly remarkable result, so which is building on earlier work by Lena Chiesa and Francis Bach. So without further ado, let's talk about machine learning and high-dimensional analysis and neural networks. So machine learning deals with high-dimensional problems. So in image classification problems, we view an RGB image with, say, 256 by 256 pixels, and we've got 3 color channels. So that gives us roughly 200,000 variables, and we view these as independent variables. So we automatically start in a very, very high dimensional space. In natural language processing, we've got, again, a dimension which is comparable to the number of words in a language, or sometimes we split up a single word into 2 directions if it has 2 different meanings, like the word ball. So in any case, we've got hundreds, thousands, sometimes 100,000 dimensional spaces. So I think a lot of the problems are somewhat similar to classical numerical analysis, but in very high dimensional spaces where we need to develop different tools. And the approach of machine learning is to leverage the enormous amounts of data that we've been accumulating in recent years. So a very sample model problem would be that we say we've got a data set of tuples xi, yi, and our task is to predict y from x. So we've got an image and we want to know, is the label 1 or 2 or 3 or 4, which would be, dog, car, cat, whatever. And so the simplest approach is to minimize this functional, which we call a risk functional, where we take the discrepancy of the output of our model from the output that we would like to see. We square the whole thing, sum it up, and we use a function class H, which is the hypothesis class. So if you compare it again to classical numerical analysis, this would be something like the choice of a Galerkin space. Now, there are, I think, 3 main components to this process, 3 main challenges. So in high dimension, even big data is necessarily sparse, because if we want to cover, say, the unit cube in RD by an epsilon net, we need 1 over epsilon to the d data points, and the observable universe has roughly 10 to the 80 particles. So even for moderately large dimension and moderately small epsilon, we're not going to get a dense cover of our data space. So if we then minimize this empirical risk functional where we use the amount of data that we've got, can we guarantee that this actually performs well on unseen data? So often data concentrates on a low dimensional part of the data space. So we are interested in models that can use this and adapt to an unknown lower dimensional manifold. But in general, in the most general case, this depends heavily on the hypothesis class H. If we've got the class of measurable functions, we can easily fit all the data points, but we don't get any information on what happens away from the data points that we already know. And so we want smaller hypothesis classes. And this is basically what we study in statistical learning theory. So this is the part that I'm mostly going to ignore. The second important question in machine learning is, okay, if we know that our data is nice. So if, for example, we know that yi, the labels, are given by some function h star of xi, then is our function class large enough to approximate this well? And this is obviously very easy if h star is linear, and then we need roughly d data. Well, we need d linearly independent samples and some more if we've got noise. But then if we are trying to solve a linear problem, then we know how to do this. If we know only that h star is in some Hölder space C2 alpha, then this is extremely difficult with hypothesis classes which are good for estimation, because these spaces, especially in high dimension, are just way too large for us to learn anything from a few data points. And so we typically use modern function spaces. So we use reproducing kernel Hilbert spaces, we use Barron spaces, which I'm going to talk about a little bit below, but we're using different function models than we would have in, for example, PDE theory. And then optimization. So if we've got a parameterized function model, so our function class is given by h of theta and of some parameter, and then x, then if we know that there is a good parameter in our function class, can we actually find that? So this is the optimization part, which I'm mostly going to focus on. So let's think about what models we usually use. A typical linear model would be to say, okay, my parameterized function class is just given by ai times some basis functions phi I applied to x. So this model would be linear in the coefficients, nonlinear possibly in x. And then the nice thing about these models is that parameter optimization is very easy. The disadvantage is that the linearity is actually a serious constraint that I'm going to talk about a little bit below. So we can think about instead using nonlinear approximation techniques, where we can use the parameter as not only as a scaling factor in front, but also as a parameter which, for example, chooses which basis function or chooses which direction something goes in. And a specific case of this would be shallow neural networks. So we've got this parameter ai outside. Then we've got a parameter wi, where we just take the scalar product between wi and x. So we take a projection onto one direction, and then we add bi, which is called a bias variable. So we apply and then we apply a nonlinear function to this, an activation function. So shallow neural networks look very, very similar to this, except that we also have this degree of freedom where we choose the direction of our projection. And this is actually a massive help. There are models where we just initialize wi and bi at the beginning. We do it randomly, and then only optimize AI, and those random feature models perform well in some tasks, but typically what we really want is the case where all the three variables are optimized over.
So there's a question in the chat or a comment, but still the approximation space is flat.
So here for these it's not. The set of functions, if I fix M, the set of functions is a manifold, because if I add two networks like this, then what I'm going to get back is a network with width 2m. So so in the end, if we take the infinite parameter limit, well, it depends a little bit on what norm constraint we put on things. But yes, in the infinite parameter limit, we're going to get a linear space. In the but for finite m, this is a nonlinear manifold. So I hope this answers the question. But basically here, because if we add two of these guys, what we're going to get back is not again of the form sigma applied to something.
I have another question.
Okay.
Is it a useful question to ask if you can optimize these projection directions?
Yes, the projection directions are typically optimized. So a shallow neural network, we optimize over all three variables A, W, B. A random feature model, we only optimize optimize A. So shallow neural networks can approximate a lot more functions, and it is essential that we optimize over the projection directions. Random feature models are much easier to optimize. So if you've got a problem that can be solved using a simple tool, use the simple tool. But typically, neural networks are more successful because they can solve harder problems, but the optimization side is going to be more complicated.
Cool. Thanks.
Could I also throw in something perhaps? So when you're looking at the data and you're making observations on proximity or closeness, those are often linear functionals. And so you would perhaps want to map linear functionals to vectors, but that's a choice of inner product. Is there something associated with that when you're choosing these spaces for projection, also a choice of inner product?
I think what people usually use is just the Euclidean inner product. So if you,
I was thinking of the inner product in the function space sense, that in the space of functions in which you're sitting, you have linear functionals, which perhaps would be an observation. But then to associate projections, you have to map linear functionals to vectors, and that requires a choice of inner product. And I was just trying to connect it with Sven's point about optimal choices.
You mean when you've got things like how you obtain for example, the labels from the data?
Yeah, actually, it's just accidentally. I was listening to a talk on machine learning just from yesterday.
Okay.
And this was exactly the point that was made about the observations are in some sense linear functionals. And if you want to do this projection step, then you're identifying linear functionals with a vector, but that requires a choice of inner product. And so it comes back to Sven's point about optimal choices of vector spaces for projection is also associated with optimal choice of inner product.
That sounds
okay.
That sounds like a really interesting question. I do believe that is probably more related to other tasks or other models in machine learning.
Go on. I just wanted to try and connect it with Sven's point.
So I think this is not. I think this is not where I'm going to go. And if it's okay, I would like to postpone that until after the talk.
Absolutely.
But
please go on.
Thank you. But I mean, it is an interesting question, and I want to do it justice, just not right now. So, and then we've got deep neural networks, which are just compositions of shallow neural networks. So graphically, we've got our input X, the red circles. then we apply a linear map that is this projection direction wix plus bi. We've got a bunch of those. Then we would sum over them, and for shallow neural networks, this guy would immediately be our output. But in deep neural networks, we've got a whole set of them. Then we do this again and again and again. So this is an alternating operation where we apply a linear map, apply a coordinate-wise nonlinearity. So we apply things once in every coordinate, and then apply the next linear map, and so on and so on and so on. And so deep neural networks are really hard to understand. And so we've been studying, I think we're starting to make more progress towards them, but we have studied shallow neural networks more. And so most of this talk is going to be about shallow neural networks. And I'm going to give one quick theorem for that this is indeed a good function class, because if we've got a compact set K, then functions of this form, shallow neural networks, are dense in the space of continuous functions over K. And the condition is if and only if sigma is not a polynomial. Because if it's a polynomial, then all of these functions are going to be polynomials of the same degree. But if we've got a non-polynomial activation function, then this actually spans, is dense in the space of continuous functions. So this is the universal approximation theorem, and it is, I like to think of it as an analog of the Stone-Weierstrass theorem, and it is about as useful in practice. I'm going to use this theorem in a proof later on in this talk, assuming that I get there. But it is not really useful in practice because it doesn't give us any good intuition on how to find good coefficients, how wide a neural network has to be to approximate anything. It is a purely qualitative statement. So especially in this talk, I'm going to focus on this particular nonlinear function. Some of the results are unique to it, others are not. But it is convenient and it is popular in practice because it is really cheap to compute. And right, the second part is, okay, let's talk about which functions we can approximate reasonably well. So instead of just having this sum here, I'm going to normalize this sum, which corresponds to a scaling of the coefficients, which we can write as an expectation over A times sigma of projection of x plus b. And we take this expectation with respect to the empirical distribution, which has 1 over m mass at all the points where our coefficients are. And then we've got a theorem, which in this version, I guess, goes back to Baron and Krasowski 2017, which says that if we've got a probability distribution on 0, 1 to the d-dimensional unit cube. So this would be something like on d would be the number of pixels, and we are normalized to 0, 1. So that would give us our RGB values. Then if we've got a function which can be written as an expectation of A times sigma of a fine function of x. So if we replace this empirical distribution by something general, and the parameter distribution has finite second moments, then we can use m parameters, m times d plus 2, such that we can approximate this function h star with a neural network of width m up to an error of 1 over square root m. So this is, the nice thing is, okay, we need the parameter, these vectors m, these vectors w scale like d in length, but we don't have a very strong dimension dependence in here. Dimension enters linearly. And we get 1 over square root m, we get a dimension independent approximation rate. So this strange function space, this space of functions which can be written as expectations, actually is a function space of functions which we can approximate well. And the proof is just using the law of large numbers. That is why we get this 1 over square root m here, this takes the role of the variance. So the proof is actually relatively simple. The big question is this a useful result? Does this function space contain any useful functions? And so if we set this space B, which we're calling barren space, as the space of functions which can be represented as expectations, and we set V to be the space of functions where the Fourier transform has a nice decay property. So this is modulus of f hat. This is not modulus of f hat squared. So it's not exactly related to fractional Sobolev spaces, but it is a slightly non-standard smoothness criterion. But we see that these spaces are smooth enough in some sense to be expressed as expectations. So we've got that this smoothness space is contained in barren space B. And the amazing thing is, for any m-dimensional subspace in this class V, we have that the Kolmogorov width of the m-dimensional space in the whole function space decays only like m to the minus 1 over d. So if we've got m parameters and we've got a linear space, then we are restricted to having this error scale like m to the minus 1 over d, whereas if we allow our directions, wi, our projections, to rotate appropriately, then we get an approximation rate of 1 over square root m. So that is why we really like nonlinear approximation here, because it becomes so much more powerful, especially in very high dimensions, where in dimension 100, you can see that it makes a massive difference. So this is, like I said, called barren space, and equipped with a norm which is just the second moments, the infimum of the second moments of the parameter distribution that is needed to represent, and representations are non-unique, so that is why we need this infimum here. But so we've got a large function space, which is hard to understand, but at least we know that it contains a lot of good functions. In particular, it contains all functions in the fractional Sobolev space of order S, where S has to be bigger than d half plus 2. So in higher dimensions, it becomes more restrictive, but less so in a sense than classical spaces. So this is my introduction to why we like neural networks, why we think they're good models. Now I'm going to switch gears a little bit and talk about optimization instead. So if there are more questions about function approximation, then I would say let's do those right now.
Yeah, can you remind me again, this parameter m, is that the amount of data points that are available?
No, so for me, amount of data points that are available is going to be n, number of, and number here for a neural network, the m is the number of the width of the neural network. Or here in this case, it was the dimension of the function space that I use for approximation. So n is going to be related to data. M is going to be related to the complexity of my model.
Okay. So if I have, so I don't know anything about machine learning or statistics. So I'm just imagining I have this d-dimensional space, very, very big, and then I have a sparse subset of n points. Mm-hmm. And then I take sort of, what are they called? The primary directions. I don't know, you do this PCA analysis, and then you maybe get an m-dimensional model. Does that make sense to think of it like this?
That makes sense. but instead of PCA, which is a linear method, we are using nonlinear methods like neural networks. Okay. So, and we are not, so PCA is a dimension reduction technique, which is great if you know that your data points live on a lower dimensional linear space, but you don't really know that space. So PCA is how you find that. Mm-hmm. There are other there are modifications that work if your data is on a lower dimensional manifold, but in neural networks, usually we don't actually try to understand where our data live. We are trying to approximate a function with respect to an unknown data distribution. So I've got this part here, where we've got a target function h star, and we're trying to approximate it in L2 of P. So P would be the unknown data distribution, and that is the thing that often lives on a lower dimensional set. So PCA tries to find P, whereas neural networks don't even try to find P. They just try to approximate this, and sort of you have an implicit process of guessing at the data distribution in there.
I see. Cool.
Thank you. I also have a question? So great summary of this approximation theory. Love that. Could you say something about how they choose sigma?
So sigma should be a non-polynomial function. There are a few popular choices. There is this Rayleigh choice, which is the one that I wrote down here. There are other versions which are piecewise linear. There are one popular version is the hyperbolic tangent. So mostly what you want is something that is really not linear and far from being linear. I think most common choices are monotone increasing functions.
Yeah, I just guess whether there was a sense of interpretation for each of these choices.
So the classical choice is sigma to be the Heaviside function, which corresponds to the original motivation of neural networks, where a neuron is either on or off, and then you take a weighted average of the neurons from the previous layers and then go with that. And that is really hard to optimize. So people started using smoothed out versions like sigmoid or hyperbolic tangent. And then people started using functions like this, like Rayleigh. And a big advantage of Rayleigh is that if with a hyperbolic tangent, you've got a very large input here, then the derivative is going to be very small. And so if you try to optimize something and you've got very small derivatives, it's not easy. Whereas here, the derivative is always 1 or 0. So that I think the interpretation is clearest if you've got just the motivation from biology is when you've got the Heaviside function. But the different choices are more related, I think, to optimization and then to an extent to empirical success in different areas. But we don't have a clear understanding necessarily what the different, or it is at times hard to capture what the different functions can do.
Yeah, I guess maybe my thought was whether you included choices within your optimization. That was what was on my mind. We don't consider optimizing over sigma. There is the possibility of including parameters in sigma and then optimizing over those. But I think that is at least not what I'm thinking about in this talk. And I think what is more often done is to try out a lot of different architectures and then choose the one that seems to perform best. So it is not, I think it is usually chosen as a hyperparameter and then the hyperparameters are grid searched. It is not part of the gradient flow optimization process. Okay, super, thanks, Stephan.
All right. So then let's come to overparameterized models and non-convexity in machine learning. So why do I say we need non-convex optimization? So we can consider a parameterized function model where we've got this general function which has an m-dimensional parameter and takes a d-dimensional input and then returns a real number. So if we assume that we've got a sufficiently expressive function models, by which I mean that we've got a model such that for all tuples xi, yi, there exists a parameter such that the function h of theta fits the values yi exactly at every xi. So this is if we've got, very, very many parameters and a very complex function class, this is to be expected. Then we can say that, okay, this empirical risk functional, where we just take the average over the mismatch between h of theta at xi and the desired output yi, this is exactly 0 at the minimum, namely exactly if all the data points are fit exactly. And under certain assumptions, we can, of course, use this function from our m to our n as a function to which we can apply the regular value theorem and Sart's theorem. And so under smoothness assumptions, generically for almost all choices of yi, the set of minimizers of this functional is an m-n dimensional submanifold of our parameter space. In particular, for overparameterized neural networks, for neural networks with very many parameters, which is the realistic case, this is a very high dimensional submanifold of our data space, of our parameter space. So we've got a function that is minimized, not at a single, where the minimizers are not isolated points, as we usually like to think, but where the minimizing set is a manifold. And in this case, we don't expect convexity near the minimum. Namely, if we look at the function 1 minus x squared minus y squared squared, which is minimized on the unit circle, then we can compute the Hessian and the determinant of the Hessian. And so at the point x comma 0, the determinant of the Hessian is 3 times x squared minus 1, which is perfectly fine. This when x is approximately 1, this is positive. And x squared minus 1. So if we are inside the unit circle, this is a negative determinant. So we are strictly non-convex on one side of the unit circle if we're close by to the unit circle. So you can see that in radial direction, we are convex, but in angular direction, we are actually concave. So convex optimization does not work, even if we assume that we start close to a minimum, unless this minimizing manifold is linear, which is only really the case for linear function models. So or models which are linear in the parameters, not necessarily in the data. But so if we want to do optimization for neural networks, we have to deal with non-convex optimization. So I said that I would come to geometry, and this is about where that happens. I might be a bit slow to go through this, and I'm probably going to skip a few things, but I'll try to focus on the main ideas. I think if you're interested in any of these things, please ask away. I think talking about the basics properly is probably more interesting than rushing to get to any of the proofs. So shallow neural networks and Wasserstein gradient flows. So if we consider a general risk functional, which is we've got our function h, which has parameters a, w, and b, which are the weights, the parameters of this neural network. We've got a general loss function L, and we've got a data distribution over the space of data points and labels, which is a joint distribution. So this is what we would like to optimize. And if we assume that this data distribution is an empirical distribution, then we just recover functionals of the form that I was talking about before, where we've got n data points. But we can also think about this as assuming that we actually have access to the probability distribution. And I prefer this notation. So that is why I'm using it. But if you want to specialize it to big data, then you just replace this general distribution with an empirical distribution, and all the integrals become sums. So then the technique that we typically use is we initialize our parameters a, w, b, so vectors containing ai, wi, and bi, and we optimize by a gradient flow, which is just the gradient of this risk functional. Here, if I take this derivative inside, then I get the first derivative, the derivative of the loss function in the first argument of this little L, which could be something like h minus y squared, but also more general. And I've got the gradient with respect to the parameter a, j, w, j, b, j, which I apply to this guy. This kills all but one term, and the 1 over m and m that I used for the time rescaling cancel out. So this guy is just minus partial 1L, or so minus the first derivative of the loss function, times the gradient of this guy with respect to its parameters, which we can also write as the negative gradient of with respect to a, w, and b of the first derivative of L at the function represented by our parameters. And then we've got a times sigma w x plus b, and we just evaluate this at the point awb is equal to ajwjbj. So we've got so we can represent the right-hand side of this equation as a gradient of a potential, and we just need to evaluate this at the point where the parameters are. And the potential obviously depends on the parameters in a nonlinear way. But so we can write this equation. So we've got the derivative is equal to this guy, and the theorem is, okay, if we've got a system of ODEs where every parameter evolves as the flow of a certain vector field, then the empirical distribution of these parameters is a distributional solution of the continuity equation, where we take ddt pi m, so derivative of the empirical distribution is the divergence of pi times the negative of this vector field. And h pi is just a shorthand again for the function represented by the expectation, in this case with respect to these finitely many parameters. I'm going to probably skip this proof because I imagine it is familiar to many people in the audience, but it is a very quick calculation where we just insert definitions and find that the flow of the vector field and the continuity equation go hand in hand by just using the definitions. And in a sense, using the flow of the vector field is nothing but the method of characteristics for this precise parameter distribution. And then there is, in the same article by Chisa and Bach, they establish that if these parameters evolve by the gradient flow of a risk functional, then the empirical distribution evolves by the Wasserstein gradient flow of the functional risk of pi is equal to integral over rd plus 1 of the loss function. So this is just basically the same functional, but we cast it slightly more generally.
Could I ask a question?
Yes.
So the gradient flow for the vector quantity AWB, you were taking a Cartesian inner product there, or a Euclidean inner product. Yes. That was the choice. So what happens if you deform away from treating A, W, and B symmetrically in that fashion and have an anisotropic inner product?
So I'm not entirely sure that anybody has looked at that. So machine learning has a lot of different optimization algorithms. Gradient descent is one of them. And typically what we do is not actual gradient descent. We use a stochastic version because we usually, I've written down this integral over Rd with respect to an unknown probability distribution. And what we typically do is in every time step, we estimate this integral using only a fraction of the data that we actually have, because it is much cheaper and it gives us a little bit of stochastic noise, which some people conjecture could be beneficial to optimization, but mostly it's just much cheaper that way.
So what is the name? What is the name for that process of just sampling from the data? Does it have a name?
People call it stochastic gradient descent.
Stochastic gradient descent. Okay,
thanks. You can also find it under mini batches. So you've got, so what we're trying to optimize, is this quantity, risk of AWB, where this is the expectation of loss with respect to an unknown data distribution. And we've got a lot of data points. So what we try to minimize in some sense is the estimation of this using all the data points. But to compute these gradients in every time step, we use a mini batch of, say, 50 to 100 data points, maybe 300. But we are doing a very coarse estimate, which I think is somewhat justified in the sense that we're minimizing the wrong thing anyway. Might as well do it the computationally cheaper way.
So maybe just coming back to my first point. So the W and the B, they in some sense are playing the same role. They're part of the affine space on which sigma lives. So treating them uniformly seems fine. But the scale factor A, that feels as if it's playing a different role. So again, in that Cartesian product, it feels like A could be demarcated from W and B.
Yes. I don't think anybody has done that necessarily. But I agree that the choice of Euclidean inner product is definitely a choice. Going back a little bit again, there are other optimization algorithms which treat coordinates differently. They are typically more aggressive than just treat it, and they may treat even different coordinate entries in WI in different ways. But if you look up probably RMS prop or ADAM, where ADAM stands for something like adaptive and momentum, something like that. These methods use coordinate-wise arguments, and they are a lot more aggressive. They try to adapt to the geometry of the loss function a lot more and not use Euclidean geometry. The great thing about these optimizers is that they are often much faster at optimizing the function that we give them. The problem is that the function that we give them is not the function that we actually care about, because we only have so many data samples. So then they may be very successful at optimizing that, but they may not be as successful at optimizing optimizing for the underlying distribution for unseen data samples. And so vanilla gradient descent seems to be doing better at that for some reason.
Thanks a lot, Stephan.
All right. And yeah, I think you could put a precondition now on A. If you make that spatially homogeneous, I think all you have to do is, change your PDE a little bit and do your Wasserstein distance differently. If you make things spatially dependent, then I would need to think a little bit about what goes through and what doesn't. So we've got a PDE description and we've got a Wasserstein gradient flow. And again, even if we take the infinite parameter limit, this functional does not suddenly become convex because we're looking at a Wasserstein gradient flow, and there is still a large amount of non-uniqueness in how we represent the same function h pi by different parameter distributions pi. So this, again, is not expected to be a convex optimization problem, even in this extension. But we can say something about convergence to minimizers. Namely, this is going to be my main result. And this is a little bit of a special case, which I think is interesting to understand already. So let's assume that we've got a risk functional where we look only where we've got no variation in the y direction. We're just trying to approximate a target function without any noise. So we've got this h pi minus h star squared. So we need, and we are trying to approximate this with respect to either an unknown data distribution or with respect to some finite amount of data. So let pi naught, our initial parameter distribution, be a parameter distribution which is supported on the whole space, which is stronger than I need. I need that it has some support in every direction, but for simplicity, just imagine a Gaussian on RD plus 2. And we let these distributions evolve by the Wasserstein gradient flow of R, which again is just the infinite parameter limit of having having a neural network optimization. And then we can say two things are equivalent. First of all, the risk goes to 0 as time goes to infinity, and h pi t converges to the target function h star strongly in L2 of p. So this is by definition, but we've got a third thing that is equivalent, which is that there exists some function g in L2 of p such that h pi t converges to g weakly in L2 of p. And this is great because the convergence of h pi t, we know that the risk is non-increasing. So the L2 discrepancy between h pi and h star is non-increasing. So we know by compactness that we've got limits along subsequences. So if we could show that this weak limit is in fact unique, that the limit is unique along all subsequences, then we would immediately know that the risk converges to 0. The problem is that this actually is not that easy to establish, and we are working towards that, but it is somewhat non-obvious to exclude cycles in the limiting dynamics. But so in a sense, we can't say that we converge to the right thing. We can't say that we converge at all. So the only condition is that risk of pi t converges to 0, so that the function represented by the distribution actually converges to the right thing. This does not say anything about our parameter distribution, and especially if the limiting function h star cannot be represented in our Barron space, then the distributions pi t would have to converge. And even if it is in the correct parameter space, then we do not have strong evidence that it has to converge. Well, numerically it seems to converge, but we don't have analytic reasons for that yet. But at least we've got a condition that if we have a weak limit, then we're good. The thing that I like about the result is that it tells us something about initializing our weights. Because typically what we do is we take A, W, and B, and we draw them from a probability distribution on the parameter space at initial time. And this kind of serves as a very weak and fairly abstract argument of saying, this is actually a good idea, and this is how you should choose your data distribution. So in a sense, this is an interesting result of saying the problem is non-convex. You totally can get stuck at points, and if you initialize badly, you will get stuck even in simulations. But there is a good way of initializing your data which helps you to actually converge the global minimizer. So that is my interpretation of the result. And the rest of the talk is going to be on the proof of that. And I think I'm going to skip a lot of that and just give one main idea. So we've got the same notations as before. One important observation here is that sigma, as I chose it, is positively one homogeneous, which means that also this potential, the expectation of this guy is positively two homogeneous because I've got W plus B inside of the one homogeneous function and the parameter A outside. And so the gradient is positively one homogeneous. This allows us to focus on radial dynamics, on what happens on rays, and allows us to reduce a few things to the unit sphere instead of having to look at the non-compact space RD plus 2. And I'm going to just summarize my weights in one vector and simplify the notation for activation a little bit. And these are the second moments of the distribution on parameter space. So then we've got two lemmas. First one is if our parameter distribution evolves by the Wasserstein gradient flow of the risk functional, then the second moments of the parameter distribution grow at most sublinearly. So gradient flow is not too aggressive at shooting our parameters off to infinity. The second one is that, okay, assume that pi naught has full support on our D plus 2, and that these functions delta pi are the potential that drives our continuity equation, or the vector field that drives our continuity equation, converge to limits. Then if the limit of the potential is not identically 0, then we know that the second moments have to blow up exponentially. So the proof is simple. Namely, we compute the derivative, we use Holder's inequality, and we see that the derivative is bounded from above by the square root of the derivative of energy dissipation. So that is what gives us this slow growth. The second lemma is more interesting. So now, and this is the only thing that I'm going to prove in detail. This is the thing where geometry comes in most. So assume that we've got a limit G that is not 0 of the potentials which drive a continuity equation. Then since we can reverse the sign in the first coordinate, we know that there exists some parameter where the limit of the potentials is strictly negative. Okay, So we can choose epsilon such that negative epsilon is a regular value of the function g of theta over norm theta squared, where this dividing by norm theta squared is just because we've got a two homogeneous function. So I'm looking at a cone. So I'm looking at a sublevel set of a zero homogeneous function, which is a cone. This guy. And we note that the outer unit normal is gradient of g of theta divided by its norm, where this is not dividing by zero because we've got a regular value. We've got some nice compactness because we only really need to think about the unit sphere. And we've got that this is the outer unit normal because we're looking at sublevel sets. And so, since this gradient is non-zero, and we know that the gradient of the potentials goes there uniformly, there exists a t greater than zero such that for all positive times, the driving field of the continuity equation and v have a positive scalar product on the boundary of this cone, using again some homogeneity. And then we can calculate the derivative of the second moments again. The point where this is important is to this positivity is to make a boundary term positive. So what we can think of is that we're looking at a cone of good parameters. We're looking at a cone where where to try and approximate a target function, the gradient flow wants to shift more mass. These are the correct type of parameters. So this is saying for large time, we are shifting positive. We are not letting mass leave this cone of good parameters. And inside this cone of good parameters, we want to strengthen the impact of that cone because we want more of that. So if the inside here is theta times the gradient, which inside this cone is driving things radially. We know that this is, because of homogeneity, the inner product between theta and the gradient of the homogeneous function is just a multiple of the homogeneous function, which, because we are in this cone, is greater than 4 epsilon times norm theta squared, which is 4 epsilon times m2 of pi t. So essentially the whole thing boils down to, we've got a cone of good parameters, and if we start with mass everywhere that is preserved for finite time, and under the convergence condition, we can identify a cone which would just be getting more and more mass and shooting it outside, leading to things blowing up faster than they can. And then we've got an argument that says there are equivalent things, namely that risk goes to the lowest possible value, and that there exist limits of the potential and of the gradient of the potential, which are driving the continuity equation, which are driving the Wasserstein gradient flow. And so compactness guarantees that these have subsequences which converge uniformly. So the question boils down to a uniqueness problem, which we hope will be a bit more accessible to further study. I'm going to skip the proof of this. I don't think I've got the time to discuss it, but it is, again, just analyzing the second moments. I'm going to emphasize this does not say anything about the convergence of the parameter distributions. Even if the minimizing distribution exists, this is purely a qualitative result for the convergence of the functions represented by those, and it is purely qualitative. This cannot be used to obtain a convergence rate, and in fact, we can show that even if our target function is Lipschitz continuous, the convergence may be extremely slow, t to the -1 over d. And there are some additional technical restrictions. I want to say that this builds very heavily on work of Lenek Cesare and Francis Bach, who proved it for smooth activation and for a toy model for ReLU. And then at pretty much the same time, we understood how to work with ReLU itself, how to circumvent the problems that are caused by the non-differentiability of the activation function sigma at the origin. And there are some extensions to other settings of this. And with that, I would like to thank you for your attention. And if there are more questions, I'll be happy to talk about that.
Thank you.